So a neutral atom walks into a bar, orders a whiskey. Bartender serves up the whiskey. The neutral atom says, "How much?" The bartender looks at the neutral atom and says, "For you, no charge." Today is my daughter Sophia's first birthday, and I felt like it just wouldn't be right unless I started this off with a cheesy quantum-themed dad joke. So you're welcome. My name is Matt Kinsella. I am the CEO of Infleqtion, and this is not my first Q2B. I've been many times in my past life as an investor, but it is my first Q2B as a part of a quantum company. And so I thought for that reason I would take this opportunity to introduce myself, reintroduce Infleqtion to those of you who don't know us, and then we'll have a little fun. I'll have some other folks join me on stage later in the presentation. But before I do that, I'd just like to take a moment to reflect as to where we are right now. It's mid-December, the holidays are approaching. It's that warm, cozy time of year where we gather with friends and family, and we gather here at Q2B to humble brag about all the great things we've done over the last 365 days. And so I can assure you my presentation will be exactly that, mostly humble bragging about all the great things we've done. So who is Infleqtion? And we went backwards here. Hold on a second. There we go. Who is Infleqtion? So we're sort of neutral atom OGs. And for those of you who don't know what OG is, that's original gangster. We've been around since 2007, and we've been a critical supplier to the quantum industry since day one. If any of you work with neutral atoms, it's likely that you've used some of our components over the years. And because of the flexibility of the neutral atom modality, we are leaders in both the quantum sensing and the quantum computing markets. And we also have a very robust software business, which we use both internally and externally, and that works across modalities, including electrons over helium. And in fact, our friends at EuroQ put this nifty little postcard in all of the tote bags. And at the bottom of that is an email address, which links to our simulation of the EuroQ computer. So if you want to try SuperStack, send a note to that email address, and we'll get you all set up. And then finally, from a scale perspective, we'll do about $25 million in revenue this year, and that's up about 2.5x year on year. So our vision is to harness the power of quantum to expand human potential. That's big, that's hairy, that's audacious, it's a little cheesy, perfect for a corporate vision. And our mission, how do we bring that vision to life, is to commercialize quantum, simply put. And so how did I get here? Well, my trip down the quantum rabbit hole began in 2017. I had been at my prior firm, Maverick, which was an investment firm for almost 19 years. And I got very curious about quantum in 2017 and ultimately met the founder of Infleqtion, then known as Cold Quanta, Dana Anderson, and was the first investor in then Cold Quanta, now Infleqtion. And I'd been on the board for the last 5 years or so, and then got the opportunity to join full-time as CEO in April of this year. And there were many versions of the world in which I would have been a lifer at my prior firm, but this is honestly the most exciting industry I have ever seen and the most exciting company I've ever been a part of. So honestly, it was actually a pretty easy decision ultimately. That said, many of you have seen this picture supposedly of Max Planck before and after discovering quantum physics, and I suppose you could say this represents a little bit how I've felt pre and post going down the quantum rabbit hole. So Infleqtion is exoterrestrial, which according to ChatGPT means we have a presence both here on planet Earth as well as up amongst the celestial bodies. So we have offices in Boulder, Madison, and Chicago here in the US. We have an office in Oxford in the UK, an office in Melbourne in Australia, and then a computer deployed in Japan. And then we also have had our technology up on the International Space Station for the last 5 years, which is really exciting, and we're actually about to send some more of our tech up there soon. And because of that flexibility of the neutral atom modality, it does allow us to make products in both the quantum sensing as well as the quantum computing worlds. And we do have quantum sensors that have true commercial advantage today, doing things in the timekeeping RF sensing worlds that are orders of magnitude more precise than anything else out there with classical technologies. And a good example of that is our quantum optical clock ticker, which we use rubidium atoms to produce. It's about a 3U rack-mounted form factor, so 3 pizza boxes, think, and it's 2 to 3 orders of magnitude more precise than the gold standard of atomic clocks that are out there on the market today. We have sold many of these to the DoD, and there are a lot of really interesting commercial use cases for them as well. And what's exciting is that if you were to open up those 3 pizza boxes inside are a bunch of lasers, and those can all be integrated down into photonic integrated circuits. And so this technology that today, well, before used to be the size of a room, which is today 3U rack-mounted form factor, will soon be chip scale. And we also have our computer scale. And we have our first customer installations in the UK, as well as in Japan. And we will be announcing more sales over the course of next year. And we have a very tightly integrated hardware and software approach, which accelerates our performance by about 10x. And we had put out some targets at the beginning of this year for our roadmap on various different metrics. But first was physical qubits. And so at the beginning of this year, we said we would achieve 1,600 physical qubits, which we announced earlier this year that we did indeed achieve 1,600 physical qubits at about 99.7% single qubit gate fidelities. We also said we would hit 99.5% 2-qubit CZ gate fidelities. And we announced earlier this year as well that we have 99.73% 2-qubit CZ fidelities. And then the natural next step when you have a lot of very high quality qubits is logical qubits, which we were excited to announce yesterday. And so I'd like to move on from the amuse-bouche portion of the presentation onto the main dish to talk about some of the things we've been doing with those logical qubits. So we, along with our partners at NVIDIA, pointed that logical qubit array at a material science application, specifically the Anderson impurity model. And what we saw was a 6x reduction in errors on logical qubits relative to physical qubits. And we needed to do a number of breakthroughs on our neutral atom quantum computing machine to make that happen. And one of those was having customized qubit arrays. And so historically, all of our results had been in your standard square array. But as you can see here, we have these honeycomb structures that are made up of hexagons as well as triangles, which was absolutely critical for the fault tolerance of the application. These are also highly high quality qubits, and so 99.48% median 2-qubit CZ fidelity, and over 99.8% single qubit fidelities. And so I'd like to invite Pranav Gokhale from Infleqtion, as well as Sam Stanwyck from NVIDIA, up on stage to tell us a little bit more about the technical specifics on this breakthrough. Pranav?
Great, thanks, Matt. I'm really excited to share from a software and applications perspective a little bit more about this result with logical qubits. And the first thing I'll say is that the translation between the logical qubit circuits and the physical qubit circuits was achieved using our SuperStack optimizing compiler. And we found that the optimization of that translation was critical to demonstrating these results. So I'll highlight 3 of them in particular. The first one is the canonical test of does a quantum system exhibit entanglement? And that's the Bell state, or what Einstein referred to as spooky action at a distance. So what we see here is that going from physical qubits, and this is a stringent test, this is the best pair of physical qubits we have, to the logical qubits that encompass all of those physical qubits, we see a 9x reduction in error. And in particular, we're able to get sub 1% error on the logical Bell state. What that means is that when you look at that skyscraper plot, the city plot on the right-hand side, going from the physical on the left to the logical on the right, you end up with these pristine bars that are 4 equally sized cities at the same, equally sized buildings at the same height. That is the signature of a high-quality Bell state. The second test, and moving a little bit closer to what end users are ultimately going to run, is known as the Gottesman random family. And this is the singular test of answering the question of, is this logical qubit machine actually fault tolerant? And we're really excited to share that there have been a number of attempts to achieve this criterion. This is, to our knowledge, the first ever demonstration of hardware that surpasses the Gottesman random family test. And this test is basically a collection of over 140 random circuits that are fault tolerant. And for each of those circuits, we find that our logical qubits, which are the turquoise dots, are lower, meaning better, lower error, than the blue dots, and those are the physical qubits, and again, compared to the best possible physical qubits. So here we actually see a 15x reduction in error. That's a 15x improvement in performance. And then the final test is perhaps the most exciting because it is the glimpse at how people will be operating quantum computers in the coming weeks and months. And this is an application that Matt referred to as the Anderson impurity model. It's a ground state solver in material science. And you can think of this as the gateway to a number of transformative applications for quantum computing for tasks like designing better batteries, designing better solar cells and photovoltaics, and even the holy grail of material science, which is designing things like room temperature superconductors. And for all of these tasks, there are fundamental bottlenecks to what classical computers can achieve. What we found is that as we ran these AIM circuits on our logical qubit hardware, we saw a 6x reduction in error with logical qubits versus physical qubits. And one thing as a software geek that I'm really excited about is that, interestingly, this application is not fully fault tolerant. It's partially fault tolerant. And so what this has done is opened an entirely new design space where software developers can come and balance between universality, that is having a full gate set, and partial fault tolerance to make sure that you have the full gate set you need, but still the error suppression that is needed to win with logical qubits today. And so altogether, this is a portfolio of applications that our existing users can have access to and can win with logical qubits today. So one thing I want to highlight is that this portfolio of logical qubit demonstrations was uniquely enabled and achieved with partnership of NVIDIA, and in particular, their Q2Q software ecosystem and the underlying GPU acceleration. And so I'll pass it over to our friend Sam Stanwyck from NVIDIA to talk about that integration and how GPU and QPU come together.
Thanks, Pranav, and hi, everyone. It's a pleasure to share the stage with Infleqtion and talk about our work together. And at NVIDIA, we've always thought that quantum computing is an important part of the future of accelerated computing, and that today's accelerated computing is essential to help realize that future. And so a lot of what we do is extending our hardware and software platforms to help our partners take advantage of GPUs and accelerated computing and AI to realize important milestones and breakthroughs in quantum. And the most important part of that platform is Q2Q, which is our open source SDK. So 20 years ago, when we were working on how to integrate GPUs into supercomputers and enable the entire world to program GPUs, we released software called CUDA. And now to enable integration of quantum computers into the supercomputers of the future, we released Q2Q. You can think of Q2Q as analogous to an open source quantum analog of CUDA. It extends languages like Python and C++ with quantum kernels, which enables you to integrate QPUs, either simulated or physical, with GPUs and CPUs. It provides a highly performant compiler. It provides optimized simulators of various flavors, and it integrates with leading quantum processors like those of Infleqtion. The most recent addition to Q2Q is libraries, which have optimized kernels for quantum error correction and solvers, which actually ended up being quite important in this work. And in this video, you can get a sense of what it looks like to write code in Q2Q. And a few of the kind of key features that enabled this, the simulations, especially the ability to emulate multiple QPUs, the optimized VQE kernels in our Q2Q solvers library, the custom gate operations and custom noise models native to Infleqtion hardware, mid-circuit measurement, and really the ability to test in simulation with a realistic emulator, and then seamlessly switch over to running on the physical quantum processor simply by changing a compiler flag or a program argument. And so enabling the great work that Pranav just told you about is exactly why we built Q2Q, and so we're thrilled to see it come to fruition. And we're also thrilled that it's going to be publicly available for everyone to play with and run their own experiments and make use of all these features in Q2Q and SuperStack. And for details on that, I'll pass it back to Pranav.
Great, thanks, Sam. So I'll put up on the screen ways to get started today. We're happy to announce that all this is live starting now. The first is the code for integrating with Q2Q. That is now open source in a SuperStack notebook, and we invite the whole world to come and test the performance of logical qubits with this deep integration with Q2Q simulators, as well as our infrastructure for submitting to our scale hardware using Q2Q. That's the first QR code. The second QR code is actually a pre-registration form. This hardware is real and it's running, and we're excited to work with the leading researchers and end users of the world to actually figure out how logical qubits can enable their workflows today. And we're excited to open this forum up to the whole world. So that's the second. And then finally, for those who are interested in the gory technical details, our paper is up on arXiv. You can go on the website scirate.com, S-C-I-R-A-T-E, to see it on the front page at the top. For those who are not as cultured, Scirate is basically Reddit for the quantum computing community to upvote and downvote papers. So you can check out our paper at the top there this morning with NVIDIA, University of Chicago, and University of Wisconsin. So I'm happy to pass it back to Matt to add anything else.
All right, well, thank you very much, Pranav. Thank you, Stan. I'll just ask, what types of things are you hoping people would do with Scale?
Sure.
Yeah.
One of the things we're excited about is we've shown a material science application that is really the gateway to better batteries, better photovoltaics, room temperature superconductivity studies. But there are more gates to add to our base circuits to actually specify the specific applications. And those gates can actually be run because we're in this partially fault-tolerant mode for the AIM circuits. So I would love to work with end users and customers who are thinking about those specific applications and go one step deeper into those applications. Even things like QAOA circuits actually map really nicely to what we've been able to run for optimization, for instance.
And from just the NVIDIA Q2Q perspective, I talked about the solvers library where the VQE function was used here. That has a lot more algorithms in it with optimized kernels, and we'd love to see people try that for different problems on a really high quality quantum processor and even write their own. So yeah, very excited to see what people do with it.
Great. And if we look ahead to next Q2B 2025, what should we expect?
I think there will be more humble bragging for sure. And things that come to mind is certainly more logical qubits. In addition, we work in our quantum software division with hardware of all modalities, so we would love to enable other hardware platforms to achieve logical qubits as well. Those are things that come to mind.
Well, I think it's been an incredible 2024 in terms of progress on logical qubits, error correction, and really high quality quantum hardware. And yeah, I agree with Pranav. I'm excited to see this scale up, go from 2 or a few logical qubits to many, and see what people can do with that.
Okay, thanks guys. And we will wrap it up with a quote from one of my all-time favorite movie characters. Things are moving fast in quantum, and if you don't stop and look around once in a while, you could miss it. A quote from Ferris Bueller. Thank you, everybody.
All right, we have a couple of quick questions.
Great, we got 1 minute, 9 seconds left, so
Yep.
time for some
So
questions.
the first one is, can I use Q2Q with Infleqtion in combination with Slurm scheduling in my HPC nodes?
Yeah, so it integrates with Slurm. It's running in that way at some HPC centers already. And so I think once it's available, that'll be a nice way to use it.
Okay. And the second one, does the implementation with NVIDIA use 2 logical qubits?
It does, yes.
Okay. All right, great. Thanks, Matt and team.
Thanks, everybody.
Yep.
Bye. Oh.